you fix your bicycle, you fix a car. Those things are all been taken away from us. The cars are too complicated. There's a little microprocessor that runs your car now. And as a physicist and as a teacher of newly minted physicists, we see the difference. This generation of children grew up with computer games. And it's different. Their thumbs work quite well. But the mechanical intuition that comes when you're, the first and second and fifth grade of just playing with your hands is gone.
And is that still very necessary? Or have we moved on now?
I don't know if it's necessary, but it's certainly a large part of my intuition of how the physical world works, and it's part of what helps me form these mental pictures, even at the atomic level. So just having that physical sense, I think, is very important. Now, it can be developed in other ways. I like to cook, and actually real cooking, as in go open your refrigerator, this is what you've got, let's see what we can put together.
As opposed to what?
Following a recipe. You start by following recipes, but in the end, these are the ingredients. Let's see what we can come up with.
Have your parents now considered that you have redeemed yourself for being the least academic member of your family?
No, the verdict's not in. I have two brothers, and they're both very accomplished. I would probably say the younger one. First, there was an inverse proportion to age as how rebellious we were. The oldest one was the apple in the eye of the parents, got the best grades in high school, is actually the nicest and most dutiful to the parents. And then I'm in the middle, and my younger one was very rebellious. But I think part of that rebellion actually channeled itself in creative ways. I think you have to be fundamentally somewhat rebellious in order to come up with something very new.
What was it? I know that you said that when you were at university, I think that Richard Feynman's lectures in physics, the text, inspired you. What was it about that?
He had a different way of looking at physics. Instead of just thinking immediately into the details of what roller coasters do, he would step back and talk a little bit more globally about what this was all about. And in my freshman and sophomore year, we used the Feynman lectures in physics. It was especially important in my sophomore year because the lecturer was not very good. He wasn't a permanent professor. He was actually visiting there. He worked on an accelerator there. And quite frankly, his lectures were very confused. And it spurred me to read the book, to try to understand, and actually help with my classmates, because his lectures were so confused. Now, since then, I read that series of books when I was studying for my PhD qualifying exam. This is beginning my second year at Berkeley. I've since reread them, bits and pieces, when I give lectures, either to undergraduates at Stanford or to graduate students. And so I go constantly back to them because even though it's, quote, elementary physics, it's not really. It's really a much deeper, profound appreciation of what it really means, rather than, okay, here's some formulas, this is how you solve problems.
You know, he said, I mean, it's a statement of the obvious, I suppose, to you, that things on a small scale behave nothing like things on a large scale.
That's correct.
Do you find that extraordinary? I mean, how could that be?
Well, I think
it's counterintuitive.
Of course it's counterintuitive, because our intuition is developed on things we experience personally. Starting when we're little babies, we hold something up,
right.
We drop it, it goes down, it doesn't go up.
And your kit sets and
right.
Sir Harry Kroto's Meccano,
right.
You know, that doesn't help you understand the small bits.
It does and it doesn't. What it does help you understand is the life-size stuff, and it builds real spatial skills, and that's key. The spatial skills, the ability to picture things in your brain are very reinforced by making things with your hands. So whether you're making things with your hands to build a little truck, or you're making things with your brain to see what a molecule might look like. It's really the same type of skill of picturing what might be in your mind's eye. So I think that's very important. But now, having said all of that, if you think about it, can we really comprehend things on the scale of the universe? Well, we don't have that point of view, nor can we really comprehend what's going on at the atom level. So one of the great triumphs in science is that we think we're a large way to, for example, how atoms work. The reason we know this is because we can predict something, and we can make a laser or a transistor, which depends intimately on our understanding at this so-called quantum atom level. And so far, it seems to work. Now, in the end, is this going to be an ultimate theory? Well, we don't know, but experience says probably not. But it works pretty well, at least in the regimes where we've tested it. But then let me go back to this. Every physicist or every scientist wants to figure where it fails, because that's the most exciting. Because then you say, back to the drawing board, but back to the drawing board in a very different way. Just as Newton's laws were superseded by quantum mechanics and by relativity, both of those theories had to incorporate what Newton found to be true and what experiment found to be true.
Nothing is wasted then.
It's not wasted at all. We still make airplanes and cars based on Newton's laws. We don't use general relativity, and we don't use quantum mechanics, and it's the best description at that scale. But those other theories blend very nicely, and they tell you when those things are going to fail, and they tell you why Newton's laws hold in a certain regime. So that's why it's so exciting. There is a discipline. You discover something new, but you can't just throw it away. It's not a fashion. You can't say, well, this century we're going to believe in this, and next century we might believe in something else. I mean, it really builds. And that's the best part about science.
There's Dr. Stephen Chu, Nobel laureate, 1997 Nobel Prize in Physics. He was in New Zealand for the Advanced Materials and Nanotechnology Conference, which wrapped up yesterday. It's 9 o'clock now.